Hello students. So in today's session we are going to see some more problems in continuity. So in the last two sessions we have done a wonderful job, like in first session limits we have completed, and second session we have got idea on continuity, and also we have solved some different problems. Now still some more problems we are going to work it out on the same concept, continuity. Okay, so we will see the problem. Discuss the continuity of the function fx is equal to f of x is equal to x plus 2 if x is less than or equal to 1, x minus 2 if x is more than 1. Okay, this is the function they have given it to us. They are asking us to work it out, discuss the continuity of the function. Okay, so whenever a function is given, first try to observe properly what is the function, okay, how they have defined. Okay, if you just see that fx is equal to x plus 2 for all the x values less than or equal to 1, and for all the values x more than 1 they have defined the function x minus 2. So that means the split took place at 1, right? The function is splitted at x equal to 1. That means I used to say every time where the function is splitted there may be a chance of the function is going to be discontinuous at that point. Okay, so that means at x equal to 1 when we are working, okay, we should be very careful. So first case what we do, for all c less than or equal to 1 we will work it out. Second case we work it out c is equal to 1 or x equal to 1, and third case we will work it out c greater than 1. Okay, right? Always first you have write the given function, given fx is equal to x plus 2 if x is less than or equal to 1, x minus 2 if x is more than 1. It is clearly defined throughout the real number system, right? So for all x less than or equal to 1 it's a linear polynomial it is, and for x more than 1 also it is a linear polynomial, right? That means the function is defined throughout the real number system. Clearly f is defined on R. Okay, so that means at each and every point of real number the function is defined. So what we can write, domain of fx is equal to R, we can write it, right? So now we are going to work it out for case 1. Let c less than 1 be any real number, c less than 1. When c is less than 1 then functional value f of c. So what is f of c? It's going to be c plus 2, because for all the x values less than 1 this is the function they have defined. So that's why f of c is equal to c plus 2. And then whether we require left hand limit and right hand limit in this place, not required, because for all the values c less than 1 the function is same, right? Only a single function it is. So that's why we'll try to work it out. Now limit x tends to c fx, which is equal to limit x tends to c, that means x is coming close to c now. That means and c is less than 1. So which function we have to take it? X plus 2 we have to take it. X plus 2. So which is equal to C plus 2 we get, right? We get C plus 2. So what happens now? The limiting value and the functional value both were same. They both were same. Therefore, limit x tends to C, fx is equal to f of C. It is true for all C less than 1. It is true for all C less than 1. That means what I can write? So fx is continuous. Fx is continuous for all x less than 1. For all x less than 1. This is the first case. And then case 2. Case 2 is very important for us. Case 2. Now we are going to work it out at the doubting point. That means where the function took place, right? So now we take let x is equal to 1. Okay, you can take c is equal to 1 or x equal to 1, no problem. Okay, let x is equal to 1. Then what is f of 1? For the function fx is equal to x plus 2, when x is equal to 1 they have given. That means f of 1 is going to be 1 plus 2. The value, it will be 3, right? So f of 1 is 3, we got it. Now whether we require to work it out left hand limit and right hand limit? Yes, because the function is splitting at 1. That means when you are coming, when x is approaching to 1 from left side, at the time the function is x plus 2. When x is coming close to 1 from right side, the function is x minus 2. So that's why we need to work it out left hand limit and as well as right hand limit. So now we'll work it out. LHL, limit x tends to 1 minus f of x, which is equal to limit x tends to 1. 1 minus, that means you are coming, the x is coming close to 1 from left side. That means the function you have to take x plus 2. So you are getting 1 plus 2, which is equal to 3. And right hand limit, x tends to 1 plus fx. That means your here x is approaching to 1 from right side. When x is approaching to 1 from right side, okay, the values, the x values will be more than 1, right? So that means you have to take the function x minus 2. So limit x tends to 1, x minus 2. So what happens now? 1 minus 2, which is equal to minus 1. It's very clear. The left hand limit is not same as right hand limit. Okay. So limit x tends to 1 minus fx is not same as limit x tends to 1 plus fx. So limit x tends to 1, fx does not exist. Okay, limit x tends to 1, fx does not exist. So what we can conclude, therefore fx is not continuous at x is equal to 1, right? So case 2 we have finished, and then case 3. So what is the case 3? We take c is more than 1. Right? Let c greater than 1 be any real number, c is more than 1. So the function is defined here for more than 1 as x minus 2. So what I can write, f of c is equal to c minus 2. Now we need to work it out, limiting value at c. Whether we require to work it out left hand and right hand limits here? No, not required. For all c greater than 1, the function is defined as x minus 2. So now limit x tends to c, fx, limit x tends to c, fx is equal to limit x tends to c, the function is c x minus 2. So you are getting c minus 2. That means limit x tends to c, limit x tends to c, fx is equal to f of c, we got it. It is true for all c more than 1. So that means we covered the entire real number system. That means for c less than 1, all the real values we worked out, and when x equal to 1 we worked out, and when c is more than 1 we worked out. That means we covered the entire real number system. Then from case 1, case 2 and case 3, what we observed, the function is not continuous at x equal to 1. That means we can conclude by case 1, case 2 and case 3, the function is continuous throughout the real number system except at x equal to 1. By case 1, case 2, case 3, what we conclude? So by case 1, case 2, case 3, what we can conclude? We conclude that the given function fx is continuous on r minus singleton 1. Okay, the function fx is continuous on r minus singleton 1. That means the only point of discontinuity, that is the only point of discontinuity of fx is x equal to 1. Right? This much we can give. So when they ask us to discuss the continuity of the function, this much we can do it. Okay, so this is a case 1, case 2, case 3. It's a very important problem. This model, okay, is very important. In case 1, case 2, case 3, case 2 we should be a little bit careful, right? Because the function is splitting at x equal to 1, we should be very careful, right? So I hope you understand this type of models. Okay, so we'll go for different types. Discuss the continuity of the function. Discuss the continuity of the function fx is equal to 1 by x when x not equal to 0. This is the question. Okay, discuss the continuity of the function fx is equal to 1 by x not equal to 0. Why they have given x not equal to 0? Because when you substitute x equal to 0 here, then what happens? In the denominator 0 comes. That means division with 0 is not possible. That's why they mention x not equal to 0. Okay, then what will be the domain of this function now? The domain of this function is r minus singleton 0. Right? Solution given fx is equal to 1 by x not equal to 0. Clearly fx is defined on r minus singleton 0. So domain of f is r minus singleton 0. Domain of f is r minus singleton 0. So then we have to work it out whether the function is continuous on r minus singleton 0 or not. That means we take some non-zero real number. Let c belongs to r minus singleton 0. Be any real number. Then what is f of c? F of c become 1 by c. Okay. So now we will work it out, limit also. Now limit x tends to c, fx. We don't need to work it out left hand and right hand limits here because the function is not changing. It's all the time same. It's a single function only. That means it's not splitted. It's 1 by x it is. So limit x tends to c 1 by x. So what you are getting? You are getting 1 by c. That means the limiting value is same as functional value. Therefore, limit x tends to c, fx is equal to f of c for all c belongs to r minus singleton 0. So what we conclude now? Hence, fx is continuous on r minus singleton 0, or simply you can say that, simply we can say fx is continuous. Okay, just simply we say that the function is continuous because it is continuous in its throughout the domain of the function. So that's why we can say that fx is continuous. So we'll go for another question. Show that every polynomial function is continuous. Every polynomial function is continuous. So we all know that what is a polynomial function. Let p of x is equal to a0 plus a1x plus a2 x square a3x cube plus so on an x power n. An is not equal to 0. Be a polynomial, be a real polynomial, in variable x of degree n. Okay, so because I have taken degree n in this place, x power n, the highest exponent of the variable is called the degree of the polynomial. Okay, this is the polynomial I have considered. Then we all know that the polynomial is defined throughout the real number system, right? It is clear that polynomial p of x is defined on R. So domain of p of x we can write as R. Okay, so domain of p of x is equal to R we can write. Now we can't work it out at each and every point, so we take let c belongs to R be any real number. Let c belongs to R be any real number. Okay, we will work at this point. Now what is going to be p of c? Then p of c is equal to a0 plus a1c, a2c square, a3c cube, so on, an c power n. This is p of c. Now we work it out limiting value. When you are working limiting value, is it necessary to work it out left hand and right hand limits? No, not required, because the function is not splitting here. Okay, so now limit x tends to c p of x. So it is equal to limit x tends to c. So p of x is a0 plus a1x plus a2x square, so on, an x power n. So we have already discussed this polynomial limit of polynomial function in previous sessions. Okay, by algebra of limits, what we can do, this limit you can apply to each and every individual term, and then when x is coming close to c, x value becomes c. When x is coming close to c, x square come close to c square, and x power n come close to c power n. So we are getting a0 plus A1C, A2C square plus so on an C power n as x tends to C, x power n tends to C power n. So, because of this, okay. Now, which is same as P of C, which is same as P of C, right. Therefore, limit x tends to C, P of x is equal to P of C. It is true for all C belongs to R. That means we can conclude now. Hence the polynomial function is continuous. Hence the polynomial function is continuous. Okay, right. So we'll go for the next. Find all points of discontinuity. Find all points of discontinuity. Find all points of discontinuity of the greatest integer function. Greatest integer function. Greatest integer function defined by fx is equal to box x. Okay, defined by fx is equal to box x. Before entering into this problem, you must have clear idea on the box function or step function, greatest integer function. Okay, three different names we are having for this function. Okay, it's also called step function because of its graph. You all know it. Box x always takes what? It is a greatest integer less than or equal to x. What this box x denotes? It denotes the greatest integer less than or equal to x. So now I just give some idea before enter the problem. We see the graph of this, the graph of box x. Box x is equal to minus 2 if you take the values minus 2 to minus 1. Just recall once, box x is equal to minus 1 if minus 1 is less than or equal to x less than 0. Box x is 0 if 0 less than or equal to x less than 1. Box x is 1 if 1 less than or equal to x less than 2. Box x is 2 if 2 is less than or equal to x less than 3. Okay, just some 5 values I have taken. Then okay, so now see that between 0 and 1 it is the value 0. At 0 it is 0 only. At 0 it is 0, it's a thick dot, but when it comes to 1 here it is a hole. Okay, it jumps to 1 here. So till this extent it will be 0 up to this extent. Next, when it is 1 it jumps to 1. Here thick dot will come and till 2, okay, it comes like this, and then from here okay, so like this we get. And at minus 1 it is minus 1. For less than 0, it is minus 1. At minus 2 it is minus 2. Okay. So this whole means is not included in the graph. You have to understand that. Okay. See that it is called a step function because of its graph. It's like steps. That's why we call it as a step function. So that means what do you observe here? See that suppose I take x is coming close to 2 now. I am just explaining it to you by taking one example here. So x is approaching to 2 now. When x is coming close to 2 from right side, when x is coming close to 2 from right side, then what we observe when x is coming close to 2 from right side, at the time the values are more than 2. The x values are more than 2. When x is more than 2, then automatically when x is more than 2, the box x value is 2 here. That means when x is coming close to 2, then the y is approaching to 2 it is. Okay. That means here this is a y only, the function. Y is equal to box x, this is. Right. And when x is coming close to 2 from left side, when x is coming close to 2 from left side, 2 minus. That means the values are, the x values are less than 2. When x values are less than 2, what you are getting? 1. That means the y is coming close to 1 here. The y is coming close to 1 there. That means the right hand limit and the left hand limit at x equal to 2 are differed. That means the limit is not existing at integers. Okay. It is the same thing for all the integers. It's the same thing for all the integers. But when you take for some other value, if it is between the integers, if you take it, then in that place it's very clear it is continuous. See that? You take between anything, between integers, if you take any value, it is continuous. But it is taking break. Okay. It is taking break at each and every integer. That means we can say that the integral points or integers or the points of discontinuity for the function fx is equal to box x. Okay. So this is a graphical way I have explained it to you, but now we will write in theoretical way. Okay. If you explain like this in PU board, we won't get the marks. So that's why what we do now, we will work it out as in a theoretical way of presentation. Okay. So clearly this function is defined throughout the real number system, right? Fx is equal to box x. Clearly fx is defined on R. So domain of the function is R. Domain of the function is R. Now we work it out two cases. Case 1, it's a real number which is not an integer. Real number, not an integer. And the next one we will work it out. C is an integer. Second case. So first case, case 1. Let C be any non-integer real number. Okay, non-integer real number this is. Okay, then f of c is what? In that case, f of c, okay, will be box c only, because we don't know exactly what is that c value, right? It is a non-integer value this is. So just box c. Whether we need to work it out left hand and right elements? No, not required, because you are working between integers. You are working between integers, right? That's why the function won't change there. So you are getting here now limit x tends to c fx. So limit x tends to c, fx is box x. So you are getting box C. That means we can conclude that now here. Therefore, limit extends to C, fx is equal to f of C for all non-integer, for all C non-integer real numbers. For all C non-integer real number. Case 2, for us case 2, okay, we should be very careful in presentation. Let C be any integer. Okay, for all non-integers we worked out here, and here we are working for integer values. That means so that we cover the entire real number system. Let C be any integer. Then f of C is equal to box C. For all integers, it is integer only. Box C is C. Okay, so why? You keep here box of -2, you get -2. Box of -1, -1. Box of 0, 0. See that included here. Box 1 is 1. Box 2, 2. That means whenever it is integer, it's an integer value. Okay, so box C is C. Now we work it out limiting value. When you are working limiting value, is it necessary to work it out left hand and right hand limits? Yes, it's required, because the function keep on changing at the integer values. That's why we need to change the function for left hand limit and right hand limit. So we'll work it out. LHL, limit extends to C minus fx. So which is equal to limit extends to C minus box x here. C minus means less than integer. No, it is less than C it is. Then what do you get? What you can expect? For example, you take the same 2 minus. When you are approaching to 2 from left, okay, at the time you got value 1. That means same thing it happens. 1 lesser you get always. When you are approaching to an integer, the y approaches to C minus 1. If x is approaching to C from left side, then y approaches to C minus 1. So see this example and write. So what do you get here now? You will get C minus 1. Okay, you will get C minus 1 because C is here, x is coming close to C from left. That means the value is less than C. That's why you can write C minus 1. And next, when you work it out, RHL, limit extends to C plus fx. So limit extends to C plus box x. C plus, that means x is coming close to C from right side. That means the value will be more than C. More than C. That means just more than C. So box gives always less nearest integer. No, that's why you get value C here. Always compare with that example what I told there at 2. Okay, you are getting C. So it's very clear the left hand limit is not same as right hand limit. So what we can conclude now? LHL is not same as RHL. Limit extends to C minus fx is not same as limit extends to C plus fx. Okay, so limit extends to C, fx does not exist. Does not exist. Okay, so the limit at integer is not existing. So what we conclude now? Therefore, the function fx is equal to box x is not continuous, at any integer C. Okay, is not continuous at any integer C. By case 1 and case 2, what do you conclude finally? By case 1 and case 2, what do you have to conclude? The conclusion will be like this. The given function fx is box x is discontinuous at all integral points. At all integral points. By case 1 and case 2, by case 1, case 2, we conclude that the function fx is equal to box x is discontinuous at all integral points, discontinuous at all integral points, right? So one of the theoretical conceptual question this is. Okay, I hope you understand this type. Okay, right? Next. Yeah, next we'll see algebra of continuous functions. Algebra of continuous functions. Algebra of continuous functions. Suppose f and g, are any two real functions, and both are defined at x equal to c, and both are defined at c. Okay. Suppose f and g are any two real functions and both are defined at x equal to c. Also, f and g are continuous at x equal to c. Then what we can write? Then first thing we can write f plus g is also continuous. If f and g are continuous, then f plus g is also continuous. F plus g is continuous at x equal to c. Okay. Second point, f minus g is also continuous. At x equal to c. Third one, f into g is also continuous. At x equal to c. Next, fourth one, even f by g is also continuous. F by g is continuous wherever, continuous at x equal to c, wherever limit extends to c, g of x is not equal to 0. And fifth thing, lambda into g is, or lambda into f, anything, lambda into g is continuous at x equal to c, where lambda is some scalar, And then you can say 1 by f or lambda by f is also continuous at x equal to c. Here also the condition, wherever limit extends to c, fx is not equal to 0. Seventh point, minus f is also continuous at x equal to c. Okay. So these are the points we can give it. So 7 ways algebra of continuous functions. I just explain first one, the proof of the first one I will explain it to you. Then you can do these things in a similar manner. Suppose we will see the proof of the first one. Proof of first one. So what they have given f and g are defined at C and continuous at x equal to C. Okay, defined at C, comma continuous at x equal to C. So what we can write, that is limit x tends to C, fx is equal to f of C. Limit x tends to C, g of x is equal to g of C. Because continuous at x equal to C means this thing, we can write it. Now we just consider limit x tends to C, fx plus g of x. Okay, limit x tends to C, fx plus g of x. We are going to prove that it is same as f of C plus g of C. Okay, so by algebra of limits, we know limit x tends to C, fx plus limit x tends to C, g of x by the algebra of limits. And this value is same as f of C and this value is same as g of C. So put together we can write f plus g of C this is. That means what I have considered limit x tends to C, f plus g of x is equal to what I got, f plus g of C. So that means what I can conclude now, therefore f plus g is also continuous at x equal to C this is. F plus g is also continuous at x equal to C. Similarly, you can prove all these things. Okay, so this is the algebra of continuous functions. Based on this, some various problems we will work it out. Okay, we will do one question. Discuss the continuity of sine function. Discuss the continuity of sine function. Okay, fx is equal to sine x. We all know that fx is defined throughout the real number system. Fx is defined on R. So domain of f is equal to R. Now we will check the continuity of this sine function at C. Let C belongs to R be any real number. Then f of C is equal to sine C. Okay. Now we will work it out limit. So it is not necessary to work it out left hand and right hand limits because it is a single function. It is not splitting, it is a single, right? So it is not changing, the function is not changing here. So for some negative values like this, for positive values like this, it is not changing. So we will work it out. Limit x tends to C, fx, which is equal to limit x tends to C, fx is sin x. Fx is sin x. Now x is coming close to C. See that here, we will work it out. Now x is coming close to C either from the right or from the left it is. Instead of doing this, what I do now, I take x is equal to C plus h, where h is a small positive quantity, I take it. Okay, small positive quantity I take it. H is tending to 0. It may be from small negative value also, no problem. H is coming close to 0, I take it. Now I put x is equal to C plus h here, right? When x is coming close to c, then what happens? H come close to 0 here. So, limit h tends to 0, sin c plus h. To understand better way, we are doing like this now. Actually, you can directly write sin c, but to understand in a better way, so we are doing like this. That means x is coming close to c, that means either from the right or from the left. So, to work it out of both, what we are doing, h is a quantity which is coming close to 0 here. So, I am replacing x with c plus h. If h is positive, it is coming close to c from right side. If h is negative value, then x is coming close to c from left. Both are together coming in this place. Okay, right? Limit h tends to 0, sin c plus h, sin a plus b formula, we all know it, sin a cos b plus cos a sin b. By algebra of limit, what we can do, we can apply this limit separately. Limit h tends to 0, sin c cos h plus limit h tends to 0, cos c sin h. Okay. When you observe here, sin c is a constant, fixed value, and h is coming close to 0, then it becomes cos 0, plus here cos c is a constant, fixed value. So, sin 0 here you get. So, when I write this, limit h tends to 0, it becomes sin c into cos 0 plus cos c into sin 0. So, sin c into 1 plus cos c into 0. So, sin c plus 0, you are getting sin c. Therefore, what we got now? Limit x tends to c, fx is sin c, which is same as f of c. It is true for all, it is true for all c. That means c belongs to R, entire real number system. Therefore, hence what we can do, hence fx is equal to sin x is continuous, okay, fx is continuous. Now from this similarly you can prove cos also continuous function. Similarly, in the same manner you can prove that cos x is also continuous. So here sin is continuous, sin x is continuous, cos x is continuous, then what else we can write? Sin x plus cos x is continuous. Next you can write sin x minus cos x is continuous, sin x into cos x is continuous, then sin x by cos x, that means tan x is continuous where cos x is not equal to 0. Okay, that means that is tan x is continuous on r minus 2n plus 1 into pi by 2, because cos is 0 at all odd multiples of pi by 2. Okay. So likewise you can write cos by sin is also continuous wherever that r minus n pi such that n belongs to z. Okay. So minus sin x is continuous, 2 sin x is continuous. Okay. So all these things you can write by the algebra of continuous functions. Okay. So I hope you understood based on this example. Still some more problems, we will work it out in the next session. Thank you.